Okay, so now we're going to take a look at inductors. Um, the next logical progression from capacitors is inductors. So we're going to look at basic inductors, types, series inductors, parallel inductors, inductors in DC, and then inductors in AC, and applications will be in your AC class. So we're going to look at the basic construction, various types of inductors, analyze the circuits, analyze the inductive switching circuits, and understand what goes on with an inductor. Okay, the terms that you need to be familiar with: an inductor, windings, induced voltage, inductance, the unit Henry, and RL time constants. And then in AC, we look at inductive reactance. So an inductor is a passive electrical component formed by a coil of wire which exhibits the property of inductance. So we can use the terms coil and inductor interchangeably here. The idea behind a coil is, or an inductor, is that as current is applied through the coil, through the windings, it produces an electromagnetic field. The magnetic lines of force then around each loop or turn of the winding of the coil effectively adds lines of force around the adjoining loops, forming a strong electromagnetic field within and around the coil. Okay, so we're looking at a device. It's an energy storage device that uses electromagnetism. The net direction of the total electromagnetic field creates a north and a south pole. So you can see here the simple illustration of an inductor and the windings. And you can see here what this is showing you is as we add additional loops, the magnetic field and the lines of force that surround the coil in all directions then multiply to the strength of the inductor. To understand the formation of total electromagnetic fields in a coil, we can consider the interaction then of the electromagnetic fields around loops. So we're going to look at just two loops. And the idea here is looking at the proximity. We're going to find out that there's lots of ways that we can increase the field by overlaying windings and putting different materials into the core of the electromagnetic loops. Okay, the effect here then causes magnetic lines of force in opposing directions between the lines of the loop. So we can see here as the fields are further spread apart, you'll notice that the lines of force here, or the electromagnetic field, does not connect. They do not interconnect. But as we move the loops closer together, as we would typically see in the windings of an inductor, the lines of force, or the fields, become integrated and they multiply. The effect is additive for many closely adjacent loops in a coil. So the additional loop adds to the strength of the electromagnetic field. So we've got a pictorial depiction here. Our actual schematic depiction of an inductor looks like this. So when you pull open a schematic, you're going to see something like the symbol we see on the bottom of the page here. So for a basic inductor, inductance is a measure of a coil's ability to establish an induced voltage as a result of a change in the current. And that induced voltage is in the direction that opposes the change in current. So the only time we get any real activity here with an inductor is when we stop and start the current flow, and we'll see that. The inductance L of a coil then at the time rate of change of the current di by dt determines the induced voltage. So we have the little V induced representation, small v, ind for induced, and di by dt, which is our calculus based representation of the change in current. So a change in current then causes a change in the electromagnetic field, which in turn induces a voltage across the coil. The induced voltage is directly proportional to the inductance L and di by dt. So our mathematical expression here, like we developed for the capacitor, V induced is equal to L di by dt. This formula indicates that the greater inductance, the greater the induced voltage. It also shows that the faster the coil changes its current, di by dt, the greater the induced voltage. Okay, so again, you can see here's our capacitive dV by dt relationship. So let's look at a simple problem here. Determine the induced voltage across a 1 Henry inductor when the current is changing at a rate of 2 amps per second. So very simply, 1 Henry di by dt becomes 2 amps per second. 2 times 1 is 2, so we get 2 volts induced when we use a rate of change of 2 amps per second. So as I said, the basic inductor, the inductor like the capacitor, is an energy storage device. An inductor stores energy in the electromagnetic field created by that change of current. The relationship here for energy, W is our symbol for energy, is equal to 1/2 times the inductance times the current squared. The energy stored is proportional then to the inductance and the square of the current. When the current I is in amps, the inductance is in henries. The energy, W, in this case, is in joules. So the physical characteristics, you've probably all seen an inductor, a coil of wire wrapped around some sort of material. A ferrous material is typically in the windings or the center part of the windings. So the core material is basically a coil of wire that surrounds a magnetic or sometimes a non-magnetic core. And we're going to find out what the difference here is when we use a ferrous or magnetic material versus air or something that is not magnetic. Examples of magnetic materials are iron, nickel, steel, cobalt, or some alloys. The materials have something called permeabilities that are hundreds or thousands of times greater than that of a vacuum and are classified as ferromagnetic. A ferromagnetic core provides a better path for the magnetic lines of force and thus permits a stronger magnetic field. So when we put a ferrous material as the core of a coil or an inductor, we get a better performance out of the coil. Examples of non-magnetic materials: air, copper, plastic, glass. The permeabilities of these materials are the same as for a vacuum. So it's just like having nothing in the middle. In the previous chapters then, we learned that permeability, we use the Greek letter mu of a core material, determines how easily a magnetic field can be established and is measured in Webers per ampere turns times a distance or a length, m, which is the same as H divided by M. Okay, the inductance is directly proportional to the permeability of the core material. So if we take a look at a quick example here, we've got 1.5 centimeter length of core material, 0.5 centimeter in diameter, and N of 350, okay, the number of turns. So in this example, we want to determine the inductance of the coil. The permeability of the core is set at 1/4 times 10 to the minus third. That's in what? That's in milli, 10 to the minus third, H divided by N. So first let's determine the length and the area in meters. So the length is 1.5 centimeters. We convert that to meters. So we move this, 3 decimal places to the left, we get 0.015 or 15 hundredths of a meter. The area is equal to pi r squared, so pi times that area 0.25 times 10 to the minus 2 meters squared, we get 1.96 times 10 to the minus fifth meters squared for the cross-sectional area. So the inductance of the coil then, L, is equal to the number of turns squared times mu times the cross-sectional area divided by the length L. Okay, so when we run these through the calculator, again, probably the easiest thing to do is enter in the denominator first and then invert it and multiply it by all of the terms in the numerator. That gives us 40 millihenries of inductance. So, determining the inductance of a basic inductor. So, the last thing we'll check out here is something called winding resistance. Every inductor has some loss associated with the resistance, okay, of the wire. When a coil is made of certain material, for example, insulated copper wire, the wire has a certain resistance per unit length. So you can see we've modeled it here in this schematic as the winding resistance in series with the inductance. When many turns of wire are used to construct a coil, the total resistance may be significant. This inherent resistance then is called the DC resistance or the winding resistance, R sub W. Although the resistance is distributed along the length of the wire, it effectively appears in series with the inductance of the coil. In many applications, the winding resistance may be small enough to be ignored, and the coil can be considered an ideal inductor. Okay, so you just have to determine by how the problem is presented whether or not you are going to factor it in or if you're just going to ignore it because it is so small. Same thing applies for winding capacitance. Again, we've got a distributed capacitance that occurs. The windings will act like plates of a capacitor. So we get winding capacitance as well. And this is a natural effect. So the winding capacitor generally is small and has no significant effect. Notice we put the winding capacitance in parallel with the resistor and the inductor that we previously looked at. The equivalent circuit for an inductor with both winding and capacitive winding capacitance is shown in the diagram. Okay, so the next thing we'll take a look at on the next one is a review of Faraday's law. What happens when a current is induced?